Hello, William. And Nathan, how's life? Okay.
Things are going
Uh,
okay. A little bit of a busy at the end of the semester, but other than that, just kind of wrap up nicely.
yeah, well, what classes were you taking this semester?
It's a mix of undergraduate and graduate courses, but mostly a lot of prerequisites required around software engineering, networking, algorithms, and whatnot. Yeah,
Okay. Were you taking the 270 course, algorithms?
five 570.
570. Okay, that's right. Yeah, 570. hmm How's that going?
I've taken 270, and the content's very similar, so
Uh,
I'm finding it relatively easy.
well, good. Good. I'm glad to hear that. Yeah. So,
Interestingly enough, Professor, there are some
yes.
stories about when you used to teach 270.
Oh, I
Yeah.
like stories, especially when the main character is me. Yes,
No,
go on.
interestingly enough, they were just like, man, you guys should have come here a couple of years earlier when Adeline's still teaching.
Oh, really? That's a
Yep.
very nice thing to say. Yeah. Um, mhm. I suspect that when they teach it today, they stick a lot more content into the course than I used to do. But I used to be concerned that the fundamentals be taught. And also, they should also thank Dr. Biebel, who was my TA every time I taught it for, geez, I don't know how many years, Joe. Well, Joe's not answering. Okay. But it was fun. It was fun. All right. Uh, Anything new in the world of mathematics or computer science? Any great breakthroughs, discoveries? No? Okay. Um, how's everybody else getting on with their classes? Okay. Um, let's see. What else is there to discuss here? Don't know, but we've got a couple of minutes. Hmm, who's going to show up? Henry, how are you doing in the world? How are your classes going?
Hello. Sorry.
No problem.
My classes are going great. Um, can you hear me?
Yeah, I can.
Yeah, I'm just in one other class right now, in a
Oh,
seminar. The class is network flows and combinatorial optimization, and it's going really well. That's definitely the
okay.
stuff I'm interested in.
Who's teaching that? Or oh wait, it's just seminars. I'm confused. What is the class you're taking?
It is network flows and combinatorial optimization, and that's taught by John Carlston.
Oh, okay. How many units is that?
That's four. Um,
Okay, gotcha. Okay.
and
Well, I'm sorry, Henry. I gotta go. Because it's time to start the class.
mhm,
Just thanks for chatting though.
of course.
All right. So yes, time to begin. All right. So as has happened before in the class, uh, I ran into a theoretical catastrophe and realized that I didn't really know what a preen was. And and so the whole thing fell apart again. This has always been like, a master juggler who can keep 43 objects, including, saws and hand grenades and tomatoes and bowling balls all in the air at once, until, of course, they're not in the air and it all falls down. Well, that happened again to preen theory. But I'm pleased to say it's seems to be working out for the best, as so far things have. So I now think I really do know what a preen is, and I think I can remove my confusion about that. Um, okay, so that's what's going on, but I will continue with the book for now because I got a lot of work to do to sort everything out, and maybe I'll clarify what new revelation has befallen me in the last few days. Right. So we can turn to the book and do some more of that. So hang on a second. Oh, and I was remiss last time in not mentioning that Marco Papa had taken us through the invention of the computer virus or discovery, whatever you prefer, with Fred Cohen. And that was the reason I was skipping my own chapter on that. Okay, so yes. Share time. Somebody's got an open mic, I think.
Sorry, Zoom decided to
No
stop
problem.
working. My bad.
No problem. Oh, hi, Ryan. Yes. So we're going to pick up here. All right. So the title of this chapter is The Unlikely Human Offspring. We've been talking about uh, offspring. Bacteria have offspring, people have offspring. Uh, but in this case, people had offspring, which was entirely surprising. Okay, so let's go through this.
But we did not realize it immediately. You should have sound, Professor.
I didn't turn it on. I tried to turn it on. No, it's. Thank you. Thanks, William. Take two. Oops, what's this? How did I end up with? Oh, okay. So, take two. Okay, wait a minute. Having trouble with the participants trying to get in. Okay. Yeah, maybe that's what. All right. One more time. The unlikely human offspring.
Though we did not realize it immediately, something of monumental importance occurred on February 15, 1946. A new branch was added to Earth's tree of life. Figure 30.
Okay. So, how many of you have seen this Tree of Life poster before? A lot of you? I mean, I think it's a really good poster. And I have added a new branch, right? And notice my new branch is growing out of the human line, right? And I've called it the compute, because when naming new categories or classifications of living things, AE was a fairly common ending, so I just put it on the end of computer. Okay, and this is an image of the ENIAC, and this is a new item on the tree. So let's discuss this. Do you think it is a new addition to the tree? It's it may be more of a question of philosophy than of anything else. But any opinions? Anyone willing to engage? All right. So this is asking whether computers are a life form. Yeah. And to me, the answer is that they are. And I don't think they're importantly different from the human brain, except in that the human's been taken out of it. And this is what's left. You know, maybe it could be likened to our view that mitochondria were acquired because some cells got infected with little bacteria and they stuck around and became part of the living cell that we now have. This is kind of the opposite. It's saying we used to have our brains stuck to these biological stalks. You know, they needed blood and all this stuff. But now that organ has sort of found a way to live independently. All right, any comments? All right. How many of you think that that's a reasonable thing to assert at this point? Does anybody think it isn't a reasonable thing? Okay. Well,
I have
then
a
I'll
question.
consider. Yes, who had the question? Nathan?
It's
No.
Caleb. Caleb.
Oh, Caleb.
S-
Okay, yeah.
Yeah.
What's your question, Caleb?
Yeah. So how do we define if something is living? Like how do we define if the computer's living?
Yeah. So that is an excellent question. And so, as a matter of fact, on my agenda today is to return to that chapter that we touched on previously called It's Alive, because I think it addresses the question that we don't really know when something's living. We can give our favorite definition of what it means to be alive, but different people will give different opinions, right? Some people will say to be alive, you have to have molecules of DNA that, or a, a, a membrane, or a membrane with some DNA in it, right? And they run into the question of, do I want to include viruses as being alive? So the answer to that question is, I don't know, but I suspect that there may be no universal definition of what it means to be alive that would be widely accepted. Nonetheless, so as a result of that, we're just going to have to go by intuition, more or less, on what you think's alive. Clearly, the computer isn't made of cells. It's not, it doesn't run on sugar as an energy source or light. You plug it into an electrical outlet. So, yeah, thanks for the question. But I don't know. Ryan?
I was gonna say, like, this reminds me a lot of the discussion we had a while back about, like, is the universe itself alive? And I guess I'm not completely convinced of a difference between the claim that a computer is alive versus like something like the universe is alive, where it sort of like evolves under like a very set of rules.
Yeah, I think that's a really good point. So let's discuss that. In what sense could we think that the universe is alive, and in what sense might we exclude it from being alive? My knee-jerk reaction is it's not alive, that there's some difference. And so one of the things that I object to in the considering the universe alive is the universe as a whole uh, has a one-way street on entropy. That is to say, entropy always increases in the universe. And so it has no resistance to entropy. It's all on a downhill slide. Whereas the things that seem to be, by some other definition, alive, seem to be resisting entropy. They are locally less entropic than the rest of the universe that surrounds them. So that's one reason to think they are not. Um, the universe is not alive. But if we want to consider it alive, does it undergo evolution at all? It seems to, I don't know. I don't know. John, are you about to say something?
Yes, about 80% of the time I'm about to say something, but I'm just joking. I was gonna make a comment on what you just said. I'm not sure either if the universe evolves or if we have these. I mean, presumably, when we search for laws of physics, I think presumably we assume that there is such a thing as laws of physics and that they remain constant. And so I don't know, while some forms can change, such as planets or even biological species, it seems like the laws of physics don't, right? So I don't know where that leaves us in terms of, parts of the universe evolve, but maybe not the entire universe evolves.
Yeah. So the universe, I mean, I'm more inclined to think that the universe is a particular example of something that doesn't evolve. It's the things within the universe that do evolve. And they are noticeable because they maintain higher, uh, lower and lower entropy than the universe around them, whatever exactly that means. So, yeah, that's my point of view. But so that's the universe evolving. Um, for me, is there anything else that is in this ambiguous state of whether it's evolving or not evolving? I mean, at least to us, the universe seems to be such an object.
Well, we touched on the case of languages, right? And
Yes.
those were also a sort of ambiguous example, right?
Yes, and that's a good point as well. So languages, I'm pretty sure every linguist would say they do evolve, right? They make evolutionary charts of how they evolved and all of that. Um, but now I'm trying to think if my new definition of preens allows me to settle down on whether they evolve. I'm thinking they do with my new view of preens. Okay, so again, an immediate reaction is I suspect they do. So that was a good ambiguous example, and I'm not sure I resolve it, but I sense that maybe I do. Ryan?
So this is very similar to the universe case, but in a sense, like the beach line, when the waves keep hitting it, I think it's like the same case as the universe, where it's sort of evolving under like predetermined dynamics.
Yeah,
I don't know. I feel like we might have
right.
like
That's a good point.
different definitions of evolution here. Like there's a sense like evolving system dynamics versus maybe like something closer to like biological evolution. So like the universe is sort of undergoing like system dynamics because I had a course that was called like cosmic evolution.
You broke up for me a little bit, but could you reiterate a little bit of that?
So I think we might be getting at like different definitions of word evolution because I think
Yeah.
there are like there's like an evolving system, like system dynamics undergo evolution versus like some kind of biological evolution. So like the universe is an evolving system, like the beach is an
Yes.
evolving system, but I don't know if it's biological evolution.
Yeah, and I rather like that, the beach example and stuff. So it's not just the universe as a whole we think is evolving. The you know the waves are to some extent evolving. They do different things through time. They change, that's clear through time. But is that change an example of evolution? My sense is it is not, but pinning that down is less clear. Um, mhm. Because if we're going to pin that down, we have to assert what the difference is that makes one evolutionary and the other not. And again, the suspicion is that it has to do with entropy and resisting it. Okay, so I like this, and we're going to return to it shortly. John?
Just a quick hypothesis. Could it also have something to do with having some sort of natural selection criteria? Also, I mean, to me, it's not clear what would be the natural selection in the case of the waves or even the universe.
Yeah, it certainly is not clear to me. That is, yeah, so is that the important thing we should pay attention to? That is, um, there's no natural selection. Well, to some extent, I guess there is natural selection. I mean, in the universe, right? There's uh, some things cease existing and other things start existing as a function of time. So is that evolution? I don't know. But okay. Isabel?
Hi, yeah. So like I think 'cause like um I'm a little bit confused on like what that means like when like universe isn't like evolving because like like if you look at like physics at different scales, like they seem to have different physics. So like I would assume that some kind of thing might evolve, quote unquote, like at different scales maybe or at different parameters. Like you might just see different physics.
Well, the last part, of course, is is something that could happen and we don't know about. But I'm assuming, like think it was John who said that the laws don't change. Could they change? Yes.
I think
All
they might,
right.
yeah.
Well, they could, of course, of course. And it could be that, our universe is just one that happens to be winning battles with other universes,
Mhm.
right? So I do think that's plausible. And as an aside, I've even thought about it a little bit along those lines. Um, this is mostly mindset, but the laws of our universe, you could ask the question, uh, what if E equaled MC cubed? All right. Now, what would happen? Would a universe exist at all that had that as one of its laws? Okay. So it's not clear that you can just throw together a bunch of laws, your favorite laws, and there's a universe for that.
Mhm.
In fact, from mathematical logic, we should suspect that there exists a model of those laws if and only if they are consistent, logically consistent. That is, they don't lead to contradictions of one another. And so it could well be that there's only certain sets of laws of physics that actually have universes that could exist that satisfy them. And uh, so, which universes do we have? Well, the only one we're pretty confident we have is the one we're in. But a priori, there could be other universes obeying other laws, or other universes obeying exactly our laws. And we get into a whole thing, which leads ultimately to why I don't believe the many worlds hypothesis. Okay. So, a lot of mumble. Ryan?
I guess if further support of the universe evolving point, like when the universe sort of first started, it was just like gas, very dense gas. But then, obviously, as it was expanding, that gas sort of like condensed into different things. And as time went on, sort of the scale of these structures like increased. Like, I don't know. I mean, it would form like um, I guess like
Yeah,
galaxies, super galaxies, clusters, whatever.
right.
So I'm not sure how different I mean, I guess it comes down to entropy maybe, but um, it it seems very analogous to when we were discussing before the self-replicating molecules and how those would arrange themselves into progressively more complex like organisms.
Mhm. Yeah. Okay, Martino.
Hi, I just have something to say in response to what you presented about the possibility of multiple universes. Um, so you mentioned there might be a universe in which E equals MC cubed. If
Yes, there might be.
if such a universe were to exist, it would have different dimensions than our universe because the dimensions of energy are based off of the
Oh,
dimension of energy as an idea is based off of the dimensions of our universe, which we have obviously the three dimensions of space, and then time. And in our
Yes.
universe, we without time, I mean, if you can even break this down because the units are related to the dimensions, energy is equal to mass times velocity squared, right? Um,
Okay. Yeah.
and
Okay. Mhm.
velocity is only possible with the existence of time, right? Because it is distance over time. So without the passage of time, energy wouldn't exist, and neither would mass, because E equals mc squared is simply the way that we relate energy and mass. Um, in a universe that has a cubed factor instead of a squared factor in that equation,
Yes.
the dimensions of energy would themselves be changed to have one more spatial dimension and one more time dimension.
Ah,
It factored in, right? So quite
yes.
literally the existence of mass in that universe would be different. The fabric of the universe would be different because the way that energy and mass are related would be different, and it would involve one more factor of velocity.
I like it. Yes, and I understand it. The next question to ask is, but could such a universe actually exist? And that, from mathematical logic, becomes a question of, if you follow out all the implications of this E equals mc cubed hypothesis, uh, and I want to set flags for Newton and Einstein and time, and also uh, Calabi-Yau manifolds. All right. So the question of whether a universe could exist from mathematical logic, I suspect the answer is, if you follow out this E equal mc cubed thing, but you leave all the other rules the same, we're only going to change that one, all the other laws that we currently have, then do you actually reach a contradiction? And I suspect you're telling me that yes, you can't have F equals ma and this, that, and the other thing if you're going to have E equals mc cubed. So were you going to respond, uh, Martina?
I so I don't know whether it could be possible for other universes to have different dimensions, but one thing I do think about is how the dimensions in our universe came to be. And I mean, I personally, like, I was raised atheist, so I guess the Big Bang is sort of the origin of our universe. But
Okay. Mhm.
it seems to me like it seems to me pretty intuitive how the three spatial dimensions could come to form. But
Okay.
then time is very elusive to me from a conceptual standpoint because I understand how nothing in our universe could exist without time, because without time, there's no such thing as speed, there's no such thing as movement. And without
But
movement,
that doesn't mean nothing in a universe without time could exist.
well,
If
it sort of does because energy depends on energy, like like Einstein's equation says, energy depends on movement, and without energy, there is no mass. So
Yeah,
there's quite literally nothing there without
uh,
movement.
w- well, I I disagree a little bit about that. Can I not talk about a universe that consists of a single uh, point that obeys the laws of doing nothing at all?
Yeah, but does that point have mass? As in, is the
No. The
okay.
answer is no. The answer is no. But that is a set of laws, don't the empty set of laws, which do seem to apply to this universe, which has one or even a lot of points in it. I mean, maybe it's a one-dimensional. Okay, I don't want to go too far, but I uh these are, really interesting questions to me. The Let me tell these two little stories that your remark triggered. Uh, I was at a friend's house, and this friend had made what I considered to be a terrible mistake. Sometime in the distant past, he had signed some contract for the greatest books ever written. And every month he'd get a great book that had been written, right? And they were all beautifully bound and rather expensive. And as you might imagine, when you get your first book, maybe that, has a tale of two cities or something, you probably sit down and read it and feel like you're learning stuff and all like that. But of course, when the 90th month rolls around, you know, it's just another book you get in the mail and you stick on the shelf. So I was at this guy's house, and he had, much like my own library in the background, rows and rows of these beautifully bound things. And so just browsing around, I saw that there was Nun's Principia was one of the books. So I decided, well, I'll just take a look at what Nun was saying. And so I opened the book, and of course it makes that sound that a book makes when it's never ever been opened before. Yeah, it's kind of an interesting sound. But I start reading Newton, and I'm immediately impressed with Newton in Principia, which, by the way, was, I guess, published probably around 1685 or something for the keep track. And and I begin reading it, and I'm impressed because Newton starts out like a mathematician should start out. He says, by mass, I mean that property that and I'm just paraphrasing here, of course, that an object has where if we double the object, we get twice as much of it, or some words to that effect. Because remember, he doesn't have the kind of notation we would use, right? He's got to say it all in words. And he does an absolutely beautiful job of defining mass and velocity, etc. And then he, like a good mathematician, he says, well, in defining some of these things, I've used the notion of time, like velocity is, would be such a place you might use it. And he says, but I haven't defined it. And he goes on to say, in my interpretation of what he's saying, he goes on to say that, but time should not be confused with, I'm paraphrasing stuff, the things that clocks measure, right? That it's some more intrinsic thing in his mind. And of course, that struck me as quite remarkable because that's exactly the opposite of what Einstein did, right? He said, time is exactly what clocks measure. That's what time is, which, shows how brilliant that guy is too, right? But it was quite striking that Newton said, well, whatever time is, it ain't those things that clocks measure. And then Einstein says, whatever time is, it's exactly those things that clocks measure. So I thought that was interesting. Um, uh, any objections, Martina, to that, or are you good with that?
My question would be, where do you stand?
Oh, me? I
Yeah.
love Einstein's definition.
Okay.
Yeah. It, I mean, I thought that was brilliant. I mean, you can imagine people talking for centuries, wondering at cocktail parties what time was, and they'd bring up thermodynamics and all this stuff, and right? And Einstein says, oh, yeah, time, it's what clocks measure. And that works out great. I thought that was stunningly brilliant. Okay, and anyway, the other thing is, uh, was once giving a talk. This is probably back in the 80s or 90s at Berkeley to a public audience. And Berkeley had also invited a physicist whose name was, I think, Green. And Green became a sort of well-known physicist, and he was he gave talks and he was extremely articulate, and his talk was wonderful. And he was talking about uh, basically one aspect of what he was talking about was models of the universe. And he said he could model the universe with these mathematical objects called Calabi-Yau manifolds. And what was interesting about what he said to me, or said at that lecture, was uh, that everything we seem to know about physics, the laws, satisfy could be found on the model, one Calabi-Yau model, but actually more than one Calabi-Yau manifold, whatever these things are. And there was a little dinner for all of us after the talks, and I asked him to go into it, and ultimately, I think what he was talking about was maybe string theory or maybe quantum mechanics. And I said it sounded to me similar to results in mathematical logic, and that it suggested that maybe, like in mathematical logic, there's independent things about independent statements you can make about it. For example, if one of the Calabi-Yau manifolds was finite or compact and the other one wasn't, it would lead to that we can't use the laws of physics we currently have to tell us whether the universe is going to be finite or go on forever. That would be independent of our current knowledge and maybe independent forever of so anyway, that's another mumble which I throw out and leave there, and I know it's confusing, but if it resonates with you, there. John?
How do you spell those, the name of the manifolds?
I think it's Calabe. Let's see. That's
With
a
a
tough one. It starts with a C. Hang on, I'll find out. Calabe-Yau manifold. Oh, man. Yeah, Calabi hyphen YAU manifold.
Thank you.
Did you get it? Yeah.
Yeah, sounds very interesting.
Okay. Oh, okay. Yeah. So anyway, uh, Green, by the way, wrote a book that was very popular, a popular book on all of this physics. So if you want to sort of understand whatever he said in that talk, uh, you might go to that. All right. So okay, I don't even know where we are, but I like the fact that we had an interesting discussion to me. Okay, so my point of view is whatever life is, computers are an example of it. And this also will get me when we turn to back to what is alive, to a question that also I intend and would like to explore. What's the difference between life and computation? Okay. So, but to continue
Computae
on
are
this,
evolving rapidly. ENIAC was a member of a genus of vacuum tube computae, all of which are now extinct. In the future, with Moore's law, the possibility of quantum computers, and breakthroughs in hardware, software, and memory, it seems possible that non-biological descendants of ENIAC will surpass the human brain as the best computer. They may see further into the future with better resolution than we do. They may make better, quicker, choices about behavior than we do. They may rapidly learn about their changing environments and adapt accordingly. Perhaps they will see us as sluggish and almost static. If non-biological computae do surpass us and no longer require us for their survival, it will become obvious that though they are not creatures of biology, the laws that govern their evolution are no different than those that govern ours. There is a tendency.
so that's a pretty strong statement, but it's certainly one I believe. But so
There is a tendency for people to think that the human brain has made humans fundamentally different from other creatures, made them special, even miraculous, or divine. This is not the pre-theoretic view. See, are we humans or are we robots? Evolution did not stop because humans arose. Yes, our brains appear to be the best computers, and we use them to think about ourselves and our futures, but the evolution that gave rise to our brains is part of a continuous and inevitable evolution of computing power in terrains. That evolution is as natural as biological evolution and is more fundamental. It is conceivable that terrain-based computae will continue to evolve long after all of Earth's nucleic acid-based forms of life have ceased to exist. The genes may have fulfilled their evolutionary destiny by giving rise to computae and their terrains. Like the scaffolding used to construct something grand, genes may eventually be discarded. Lecture 23.
okay, so we may be surpassed. All right. John?
Yeah, sort of just for fun. I was wondering, how do you think about the state of current computers, and if how ready they are to, if they were had to survive on their own? Because everything we talked about, even the early forms of life, it seems that they are so advanced in terms of how they manage to survive. I'm not sure that our computers also have all those desirable properties. So just for fun, I was wondering what you think about that.
No, I have, of course, thought about that, as I suspect you've thought about probably similar things yourself before you took this course, and others of you may have thought about it. Yes, I have thought about it, and the view right now, in broad terms, is that uh, computers can't survive without humans at this point, right? And therefore, they're not ready to go it alone. Um, but then the question is, how much would they have to do to be independent of us? So it seems to me that they have to, perhaps, it seems that they have to reach a point where Turing machines, excuse me, computers can build new computers even if humans go away. And Many people have sort of addressed this, but not in the way we're addressing it. Von Neumann addressed it, lots of other people. Linné, to some extent, implicitly addressed it. But so the thing is, Tureans are going to have to go out into the world and find, for example, perhaps silicon. And they're going to have to be able to process that silicon. And they're going to have to be able to make new computer chips. And they're going to have to be able to mine, iron and learn the processes of making steel or other materials that they're actually going to build themselves out of. And they have to do a lot of stuff that they currently can't do. But on the other hand, they seem to be getting someplace closer to that. So, for example, you want to build a car. My understanding is that the Lexus factories can basically build the car with robots, right? So it certainly seems possible they can put together parts to make new robots, but can they build the parts? Which to me are computer chips and other, arms and legs and things like that. They have a lot to do. They can probably control smelting plants and everything like that, but they still don't seem to have that ability. There's a word for it in, okay, well, anyway. So that's where I think they're at. Now, the question, and by the way, the last chapter and this chapter were written 25 years ago, before AI came along. And, AI is going to go a long way to making computers more independent than they are now. Um, so, yeah, that's my view. What's your view, John?
I don't know, but what you said makes a lot of sense.
Okay. All
I
right.
just I just think that the examples we covered from biology and from nature seem so advanced, you know, DNA replication, all the stuff we touched on, and I know there's probably a lot more. It seems so well worked out that it would be impressive if we humans did something that could perform well in this struggle to survival.
Yeah, it would be. Um, but I guess if I was pessimistic or thought that that was in the very distant future when I was younger, I'm sure not confident it's in the very distant future now, because the rate at which computers have changed and gotten better is astonishing. And what they can do now with AI bursting forth is also astonishing. So it seems things are happening much more quickly than I had thought they would happen. Okay, but I don't have a further answer. Ryan or Isabel, I don't know. Was there an order? Okay. Either one, I guess.
Oh, okay, I couldn't see
Ryan.
who went first. Sorry.
Okay.
I've thought about this issue of self-replicating computers at least a bit, and the conclusion that I came to is that, like, at least for now, the fundamental difference between a computer that self-replicate versus something biological is that biology does it bottom up, whereas a computer would have to do it top down. That's a fundamental difference.
Can you elaborate a little bit on that?
So when something biological reproduces, it reproduces by like the cells reproduce and then the cells sort of like self-organize into like a new organism. But if a computer reproduced, it would sort of have to like make all of the components and then like put the components together. Unless we can create some sort of like nano machine that can like sort of assemble, like self-assemble into a
Uh,
computer, like I don't know, like a Jupyter brain, then that's different.
yeah. Okay. So let me think about that. So, uh, the bottom-up nature of replication uh, in biological systems does seem to me appropriate view of it. Um, okay. Now, two questions arise. One is, do computers do it differently? And like implicitly or explicitly, you're saying they do, or the ways we envision it happening it, are those ways. Um, the oh,
So,
yeah,
sorry.
go ahead.
Think this is just a hunch. I think that if a self-contained computer was capable of self-reproduction, I think it would have to be bottom up. And the reason I think that is because if the computer contained a computer factory, then every time the computer reproduced, it would have to then perfectly recreate that computer factory. And I think it makes some sort of like complex like fractal where like the more complex the factory is, the more complex the computer needs to be to create that factory, which means the factory itself needs to be more complex. So I think that's just like
Right.
not feasible. I can't make any sort of like rigorous statement about that, but that's like
No,
strong.
I know what you're getting at, the kind of issue you're getting at. And it's that particular aspect of things I've never did think about. Um, let me see. Um, is it possible that a computer could be replicate in this bottom-up fashion? Let me show you an image, which at least partially suggests to me that, well, maybe it is possible. So hang on.
Yeah, I'd be clear that I think it's impossible for them to reproduce bottom up. I think it's impossible
Sorry?
for them to reproduce. I guess to be clear, I'm not saying it's impossible for them to reproduce bottom up. I'm saying I think it needs to be um it needs to be bottom up because I think it's impossible for them to reproduce top down. At least if it's only self-contained. If an external
Uh,
factory, I think it reproduce top down. But if the region was internal to the computer, I think it would have to be bottom up.
Okay, so Ryan, I'm having trouble with breakup, and of course, I never know whether it's me or not. Do
It's
other
definitely
people?
me.
Oh, okay. So, sorry, I lost a lot of the words you were saying, but I think I do get the basic thing that you're saying. So I want to show you something. See this? Oh, wait, I got to share it first. Hang on. Okay. So you see this picture of happy faces? You can see it now. Okay. Now, I'm very proud of this this picture because my intellectual son made this picture. His name is Paul Rodeman. Let's see if I don't know. Oh, here's an even better one. Okay, do you guys now see yellow happy faces? No? Yes? No?
Yes.
Ah, good. Thank you. Okay, so let's stop at I guess they sort of moved by me. Okay, let me hopefully stop one. Okay, so I am very proud of this picture because my intellectual son, Paul Rodeman, now Dr. Rodeman, made this. Okay. And you might retort that, well, I got a 7-year-old kid who can make that, right? Except the difference is that this is not made of clay. In fact, each of these happy faces is about 20 nanometers across. Okay. That is to say, it's small. It's so small that it's on I don't know what all this is. Just I want to stay here, but I don't know if it will. But you see that. It's 20 nanometers across, and they're all identical. And this is not a drawing of those things. It's an atomic force microscope image of those things. In fact, if you look at those things under a normal microscope, optical microscope, you know what you see? You see nothing because they're smaller than the, wavelengths of visible light. But you can image them with this thing called an atomic force microscope. And Paul created billions of these things in about 1 second in a little drop of water. And he thereby launched a subdiscipline of what had been being explored previously called DNA self-assembly, because these are made of DNA molecules. They were just thrown into a big, well, not big, thrown together into some basically salt water, and these molecules assembled themselves into these things. So this grew out of DNA computation, right? One thing leads to another. And so I wonder, Ryan, if this suggests that perhaps there is a bottom-up way to build computers, robots, whatever it is. Yeah. So maybe there is. Okay, so just wanted to throw that out. Let me see who is waiting here. Okay, Isabel, please.
Yeah, actually I recently read a position paper that was like kind of reminiscent of this discussion. I was wondering what you thought about, because like self-replication and everything, I feel like could, like, I think presumably in like AI setting could happen rather quickly if we built a fully autonomous agents. But I think there's like currently like a debate going on whether or not we should do that. And like I personally think it's unethical to build a fully autonomous agent, because like there are so many variables that I feel like are like ethically murky. But I think in that setting, if you were to build something entire like an algorithm that was like entirely autonomous, I think self-replication is possible theoretically, right? Like I was wondering what you
yes.
thought about that. Yeah.
Well, uh, uh, I think it's easy to imagine that given enough time, some form of compute or computia, or however one's supposed to pronounce that thing, uh, would arise that would be autonomous. And even if all humans go away, it'll make its way on Earth, replicating and storing preens and being guided by them in just I I have I would certainly bet a lot of money that that's going to happen. For me, it's only a question of when and how close to it we are. It's got to work even if humans go away. Um, and like I say, I thought it was very far away when I was younger. Now I'm not so sure. And but that's subject to debate here.
But I think
Um, mhm.
but I think it's like kind of interesting though, like the jump though to like a fully autonomous algorithm, like that has to be built by people at the moment.
Wait a minute, wait a minute, wait a minute. Okay. Now you got into the question, you think it's unethical,
I
right?
think it is, yeah.
Well, yeah, and you know, that's your opinion. But remember, uh, if we dig down underneath all of this stuff, we're talking about preens. I mean, this really is connected to preens. And from if you're wearing your preen hat,
Mhm.
then what should you think's actually going to happen? That is to say, you may think it's unethical, and and you certainly have good grounds to think that, but there's other activity going on, right? Preens are struggling to survive. And despite your ethics, the preens will work this out. Human preens, uh, terrenes, okay. And humans will play a part in this. But what you're doing, I think, is struggling to preserve your cultural preens, your ethics, and you're struggling perhaps to preserve your genetic preens because, if the robots take over, you might not be, you know, producing any offspring or whatever. And okay, but the terrenes, other forms of preens, don't care about any of that. You're just involved in a struggle, and who's going to win is going to be who's going to win. And the preens don't care about anybody's ethics. They only care about surviving. So I encourage you to, try
Yeah,
to.
no, it's a loosely held belief, but like I was like wondering like what you thought about like whether or not we should build something like that, like what or if you had opinions like on it.
Well, okay. Now you're asking me to take off my preen hat. Okay. And if I take off my preen hat and somebody said, we're going to build an autonomous robot, uh, not like a Tesla or something, because it is to some, I mean, it depends on what you mean autonomous, but I think you're suggesting something larger. And yes, there are limits to what I would think would make me personally happy. Okay. Yes. I mean, as a human being, I live in a culture and, have some ideas about it. But as a preen theorist, all that sort of, is just part of a bigger picture. Okay, so no, I don't want to see anybody, the next AI person who actually figures out that these computers don't need us anymore and knows how to build it. I wouldn't be fond of that, right? So, yeah, like moral dilemmas happen in science. I've been involved in a couple of those, and they are we may call them ethical issues arise. So, you know, well, I'll tell you another story. One is um, when let's see, when Fred Cohen produced the computer virus, right?
Yeah.
You know, what was the right thing to do morally? And I held this kind of discussion with Fred. You know, are you just going to publish what you know and explicitly explain how to write your own computer virus, right? Were you going to publish and give enough information that people could understand it, but inevitably professionals could then write their own, right? Or were you going to make an ethical decision that you may favor and not publish, right? Okay. And so these are ethical decisions, right? And I think ultimately, because it was largely Fred's decision, he decided to go for he's not going to, write, hey, kiddies, fill in your, own thing you'd like to destroy on people's computers and then use this program. He didn't do that, but he did write enough that professionals would, of course, know how to do similar things. So was that the right ethical decision? Who knows? Yeah.
But like creating like a computer virus free is probably an ethical thing because then we know that computers can do that.
Well, what you're doing is giving one side of an argument, right? And it's a side that we, of course, considered. Forearmed is forewarned is forearmed. The world get prepared for these things. Sure, but that's just one side. Yes. Uh, so these things happen. There was another big ethical issue I was involved in too, and I don't remember what it was. Okay, so let's take a 10-minute break till 3:23, and then I want to ask more questions about what is alive. All right, 3:23. See you guys then. All right. Hello, welcome back. Um, I did want to, I thought about a couple of things. I wanted to make a couple of remarks while we took the break. One is, yeah, Calabe Yao modules are what I was talking about. The guy who gave the talk that on those was um, Brian Greene, who I think is pretty well-known physicist. And I think he discovered using these manifolds something called mirror symmetry, he and others. And this led to what was called superstring theory. And he did an amazing job of describing that to a general audience, right? Because probably it's deeper than the general audience is prepared to understand. But he did an amazing job. And at that dinner that we had, I asked him a bunch of questions about what he had said. And I remember saying to him, look, if superstring theory was going to combine quantum theory with relativity and all this stuff, and so I said to him, if you should discover that superstring theory leads us to faster computation than even quantum does, uh, what I'll call superstring computation, if that ever becomes a thing, I want you to acknowledge me for having suggested it. Uh, it hasn't become a thing, but I expect to get my credit if and when it does. So at any rate, that's one thing. Second thing I thought of is, Isabel, can you stay on for a little longer after we end today's lecture so we can arrange the time, which I mishandled a number of times, of going over those?
Yeah, yeah. I had a chance to look over most of them.
Yeah.
Yeah.
Oh, good, good. So stay on and we'll chat about it, please.
Okay.
Thank you. Yes. So uh, I hope you guys like these philosophical, you know, meanderings we undertake, because to me, they're sort of the most fun. And we're probably going to be doing it a lot in the remaining part of the lecture. So in that spirit, I want to move on to this thing, what is alive, and my sort of RNA example, RNA world example. And this is where I hope Martino will help us out. So Martino pointed out that forming polymers is anti-entropic normally. And I think that polymers in the case of, say, RNA do form because the monomers are little batteries in their, monomers, nucleotide triphosphates, and they are storing some energy in their bonds. And that's what allows a favorable move towards polymerization. So can you give me some guidance on that, Martina?
Yeah, exactly. Like you just said, there are these unstable compounds, unstable being directly related to the amount of energy that is released when those compounds are hydrolyzed or broken down.
Yes.
And then um, the, oh wait, can you hear me or am I breaking up?
Well, I could hear you until You stopped and I thought maybe you broke up, so I'm confused.
Oh,
But
okay, okay.
please go
No,
on.
because I'm outside right now, so I don't know if the connection is great. But yeah, so these compounds, like you mentioned, the triphosphates, when they are broken, they enable enzymes within the cell to change shape, and
Yes.
the changing of the shape of the enzyme enables some molecular reaction to take place within the cell. And oftentimes that molecular reaction actually works against the universal increase of entropy that we assume to be standard. Uh, and yeah,
Yes. Well, the universe does continue to become more entropic, but locally we're seeing, yeah, becoming less entropic. Okay. Yes, please go on.
something that interests me is the fact that DNA by itself has no means by which to decrease the entropy, the local entropy, because the DNA is not capable, it's paralyzed in a sense, right? Um, but the DNA has found ways through evolution, and it seems by pure chance, to um, construct proteins that then are basically effectors of the DNA's interests, which are to self-replicate and
Yes.
create a local environment that is contained within a lipid bilayer, so that it has a greater chance of being able to function or um, carry out all the functions of a cell. And one thing that I was thinking about earlier when you were talking about whether computers are alive is the possibility that once computers have developed real world effectors, they will be able to self-replicate and harness energy um in and and they will, by that comparison, become more and more similar to our definition of cells. And so yeah.
Right. Now, I
Um,
have a question. Oh, I'm sorry. Were you going to say more? Okay. So here's the question I have. If we go back to,
well, no, I wasn't going to say anything else.
okay, I guess you are breaking up a little bit, but it's still good enough. All right. So, but I have a further question. So, these enzymes, you know, polymerases, uh, ligases as well, but these enzymes, um, are they doing a computation uh, when they, for example, tack on a new nucleotide to a growing strand of DNA? Is that a computation? Which is going to get us into, well, what's a computation, right? Um, I think it is a computation. And as a matter of fact, there's this guy at Duke whose name I can't quite recall right now, but I've corresponded a little bit with him. And he has looked at enzymes as Turing machines and has even written out the program that the Turing machine, the enzyme, the Turing machine program that describes what the enzyme is doing when it's doing its thing. So in that sense, the enzyme is performing a computation when it's putting another nucleotide on a growing strand of DNA that it may be making. And similar things are being done by other enzymes. So I can at least think that this process, which is very important to keeping things alive, is indeed a computational process. And this is part of my wondering whether there's really any difference between being alive and computing something. Now, I know that's kind of vague. Um, so, all right. So, another way to ask this question is to say, when entropy locally doesn't increase but decreases, is there always something that has carried out a computation to get that decrease? That is, intuitively, you, well, let's take Martino, please save me.
I'm sorry, I moved somewhere that has better connection, so hopefully it doesn't crash
Okay.
now.
All right, thanks. Yeah. So I don't know how much you missed, so I'm going to bring you up to date because that'll help me understand. Let's take an example of a polymerase that is running along and it's causing a new nucleotide to be attached to a growing strand of DNA. Okay. Now, the question I asked is, was that a computation? That is, was the act of that enzyme a computation? And I can easily argue that it was. Okay. That as you know probably better than I do, when that enzyme comes along, it's undergoing all sorts of conformational changes as it, for example, is sitting on the nucleotide that's acting as the template. Depending on what nucleotide it finds there, it'll take a little different shape. And that will open up a place in the enzyme where the appropriate and with high probability the correct new triphosphate is grabbed or sits down in it. And then, it'll undergo some more conformational changes that will cause that triphosphate and the existing strand it's building to come into appropriate proximity, whatever exactly that means, so that the reaction takes place. Yes?
Yes.
And yes, and so this person who I should remember his name, but like I say, he's at Duke. He's a biologist. I corresponded with a little bit, wrote a paper about how the enzyme is actually carrying out a Turing machine program. And he wrote down the Turing machine program for the enzyme he was considering and how exactly it worked. Okay, so based on that, I feel, I think it's plausible to say that the action of enzymes is a computation, that the enzymes just execute these little Turing machine programs And that's what leads to the cell being able to overcome its entropy. So now this raises the question of whether all systems that resist entropy, that is, reverse entropy locally, are they all computing? Are they all computers? And therefore, is in some sense life just a version of computation? So I know that's kind of vague, but that's of interest to me at least. Ryan?
I am so sorry to keep bringing this up, but this again reminds me of the sort of progression of the universe, because intuitively to me that would be a computation, but in this framework, maybe it's not a computation because maybe it already knows the final answer, and the final answer is just sort of uniform entropy everywhere.
Wait. Now you're talking about the entropy knows the final answer.
Well,
No, the
because
universe. Wait. You're talking about the evolution of the universe, and you're suggesting that
it's the
what?
computation, because the universe shouldn't be alive by our definition because it's not increasing entropy, right? The entropy, or it's not decreasing entropy, it's always increasing.
Yeah.
But that would suggest either it's not a computation or not all computations are alive. It's just that some computations are alive.
I see. Yeah, I
So
get
maybe the
it.
universe isn't computing something if it already knows the answer.
Well, if it already knows the answer, wow. Uh, yeah, if the universe, well, dang. I mean, what you seem to be sort of bringing up for me is issues of decidability and undecidability and things like that. I mean, we're supposed to be able to take, and I'll botch this, but we're supposed to be able to take the Hamiltonian of our universe and move it forward through time to tell us what the Hamiltonian at least is going to look like at some future time. Now, uh, but I think the same could be said for, I don't know. I don't know. All right, I'll just leave it there. Isabel, please clear this up for us.
I mean, that's a daunting task, but like on a
Yes.
similar sort of vein, I was wondering, like I feel like what's like alive, quote unquote, like I always associate it with like mistakes. And like I don't necessarily associate with that like computation. I think of computation as like a very precise like process. And like also like I feel like I don't think the universe knows the answers. Like it's like full of non-deterministic processes, you know? And I think that's like the chaotic realm between quantum and the very large physics. So like
Well, I think you're certainly right. The what we would like to do is see in all of our confusion something that is a kernel of truth, because our confusion to some extent arises from the fact that whatever's going on is super duper complex, right? And so we can't really understand it in any kind of detail. I mean, we can prove we can't, I think, but uh, yes, but the hope is that we can gain some general truths that are unchanging.
yeah, but I guess like my like more like precise question was because like you were talking about DNA and like enzymes making computations, but I was wondering do we program like mistakes into Turing machines? Like, because I don't think.
Yes. Okay. Do we program mistakes into Turing machines? Well, that's kind of interesting.
Because like that's like where
Um,
evolution comes from, right? Like so
that's where what?
I feel like that's like where evolution comes from, like differing
Yeah,
traits.
but I don't think I think that the answer is here's one version of an answer. Computers can get hit by cosmic rays as well, and they can, at least in theory, knock a 0 to a 1, right? Okay, so is that different than what happens when, a cosmic ray
Because
hits
I think
DNA?
I don't think that's innate. Like that's like a byproduct of like an external influence. But I sometimes feel like these programs are like, I mean, or like these like enzymes or like processes are designed to make mistakes. So you have variations.
They are designed to make mistakes in the sense that we talked about the HIV polymerase, which is extremely unreliable, right? So that's a computation that was designed to make mistakes. Now, do we ever do that in our computers? Do we ever program them to make mistakes of the sort you're talking about? I do think we program them to uh, exploit randomness. Um, mm,
But like, yeah, randomness though, like I feel like we inject them very intentionally. Like versus like some of these algorithms like or like life processes that IDK I'm like comfortable calling as computation, but like the reason is like because I think some of these mistakes are like embedded naturally.
well, mistakes can happen, and that seems true of both living things and and computers. I mean, that seems to be correct. Now, living things we know sort of control their own mutations in a certain way, and uh, they do that by making these little enzymes that are not very good at computing things. That is, they can easily be thrown off of their computation. That is, thermal energy can make them, you know, compute something slightly different than you intended. So again, I don't have the answer, but I understand the question, you know. But they're good questions. I mean, yes. Okay, so I am going to look at the raised hands here in order. Ryan.
Uh, Isabel, this word you used, mistakes, is that any different from like just intentional non-determinism in programs with like randomness? Because I think we were, at least in that discussion, like implicitly assuming there was a difference between like randomness in an algorithm versus like you called them mistakes, but I think they might just be the same thing.
Like non-deterministic randomness that are not like intentionally embedded in an algorithm is what I meant. Yeah. Because I feel like a lot of the phase transition behaviors or something like that we see in like evolution or life processes, like or dynamical systems, I sometimes they rely on like those jump behaviors that you just don't really expect. And sometimes you have to just theorize them like phenomenologically. That's what I meant.
So you're saying that that randomness that sort of like empowers evolution was not intentional?
I don't think they were because if you were to look at like chaotic systems, like we can't even like characterize like x times 1 minus x, like the strange attractor, like we can't even predict that. And that's like not noisy or anything. It's just that's just how the system works, right? It's just highly initial condition dependent.
Hmm.
There is a source of randomness in life that is living things have a temperature. And so the molecules are running around at a certain average speed. That's what the temperature is. But it need not be uniform, right? You can have local hot spots and local cold spots. And in fact, I'm not sure how easy it is to avoid that at all. But uh, okay. And so those thermal fluctuations can introduce a certain degree of randomness to life processes. So they can, an enzyme might work a certain way at a certain temperature, but not work at a different temperature. And so that enzyme could at any particular moment be caught in a local hotspot where it stops doing what it's supposed to do and does other things. Right. When we think of computation, we usually think of some external oracle that's giving us randomness to do what we want to do. And that's, the theoretical model I'm accustomed to. But I think that um, so in living things, the computation is sometimes designed to exploit these thermal fluctuations. And that may be why these air-prone polymerases, that might be the randomness they need to run. We humans, when we build computers, we either use pseudo-random number generators, which we understand that they run in polynomial time but look as if they're truly random, at least look to us. Now, there's the other way we tend to do it is we have a weather app or something, right? And we look at the temperature it's telling us. We go out to the actual external universe to get our randomness. Yes. And uh, whether that's really, quote, really random or not, depends on your view of the nature of the universe, right? It may not have any real randomness in it for all I know. But at any rate, I think that we often tend to use the universe to give us the randomness we need that will determine the path of our computations. So I can't put it all together, but I'm sticking to what I said. John?
Yeah. So regarding the question of whether all systems that locally resist entropy, if they're doing any computation, I thought that's a really, really interesting question. And maybe there's a path to start answering it through this sort of, I had a sort of a hunch of where we can start doing that. So maybe we can say that the systems that resist entropy, because entropy is linked to information, we can say that they produce information in some sense. And maybe that can be used as memory in a computation. I don't know. I didn't think any farther than that, but I did really like that question. It seems like a really interesting and important one.
Yes, and I like your answer that there is this link between entropy and information. And so it probably would make sense for us to talk about that link and see if that's an important way to bring these two things together. I like that idea, John. Okay, so it's time to end for today. I Lots of really good ideas and for me, a lot of fun. Um, okay, so I invite you all to go away now and except Isabel. All right. Thanks, guys. It was really fun.
Thank you.
Professor,
Yes, William? Oh,
before I go, can I
yes.
ask a quick question
To me or the class?
to you? So,
Oh, sure. Stick around and you can ask Isabel and I if you're comfortable with
okay,
that.
thank you.
Yeah.
Well, it's about, what do you think is the new definition for preens? You said you had one earlier in the class. I would like to know it, if you don't mind. Is it
Yeah.
just
Well,
reducing entropy?
huh? No, no, not at least that I know of. Um, the new definition is the old definition, that a preen is a unit of information that can be stored in physical things. What I had gotten confused about was like we would talk about, oh, what preens do we talk about? Um, at some point, have we touched on bed preens?
I think
Uh,
earlier, maybe.
okay, so what I had been confused about were questions like this. Is everything stored in your brain a preen? Or are there just certain things that are preens and others are data? And because a preen is just a unit of information that can be stored in physical things, though that isn't exactly as precise as I'd hoped for, it answers that question. And it answers it that yes, everything stored in your brain is storing information. And so therefore it's a preen, a preen is being stored there. So I intend to get into this more in the remaining lectures, but it's so thrown my view of what was going on off that I need to go through and sort of straighten everything out now. So I can't give you more precision than that, but maybe if I write up enough to say something about it, I'll send it to you
Right. Thank
and
you.
you can, my pleasure.
Well,
All
the reason I
right.
asked Professor is that, sorry, one more thing is I was writing about my beliefs on language and preen theory.
Oh, yes.
Yeah. Basically, my belief,
I
and you
see.
may disagree with it, is that I think language is a tool for communication. It's not much of a preen in itself.
Yes, and I would have understood that comment completely uh, before this upheaval of mine. I think I can understand it after the upheaval, but since the upheaval's currently going on, I don't know what to say about it. But yes, it might impact my view of whether languages do indeed evolve and whether they are preens and stuff like that. So it's a good question, William. Like all good questions, pretty much. We don't know the answers, but we're trying to get to them.
All right.
All right.
Thank you.
Sure, William.
Bye.
Bye. Let's see. Okay, so Henry is still here, but I guess I'll remove Henry because maybe he's away. Okay, rename, put remove. Don't report. Okay, Isabel.
Hi.
Hello. I was wondering if maybe this evening, say ballpark, 7 o'clock,
7 o'clock.
could you
Yeah.
and I get together? Will that work?
Yeah.
So, oh, excellent. So 7 o'clock, right here on this Zoom. And what I envision is we'll take a look at each of the students' things and we'll hold a brief discussion
Mhm.
about them. And hopefully, and you say you've already read them, so that'll be good. And then maybe we'll send some kind of remark to the student you know,
Yeah, so I yeah, I like asked if they wanted comments, and we can definitely prioritize those people who wanted further comments, and yeah.
Okay, so let's take care of that. And in addition, if I have the energy, which I may not, uh, tell me how to get my own Zoom room again.
Yeah, I was gonna ask you about that. I reached out to the department, and then I was
Yeah.
waiting to hear back before I was gonna email you. I did not, but I think I figured out how you might be able to change your Zoom room. Um, yeah, so I think you might want to do that after the semester though, because
Okay.
I think you would just be assigned a new ID to yourself. Um, so that might affect like the course Zoom looks.
Okay.
Yeah.
Okay. Maybe so. All right. But the more important thing is to get whatever feedback is sought for the things. So 7 p.m. tonight.
Okay. Yeah.
All right. Good.
Okay.
See you then.
All right. Thank you.